Courts do not decide on stories. They decide on evidence. In criminal trials, narratives may change, witnesses may forget, and testimonies may conflict. What remains stable is physical evidence. Objects, marks, measurements, and traces do not lie in the way human accounts sometimes do. Forensic physics applies the laws of nature to crime scenes. It transforms physical traces into evidence that can stand scrutiny in court. This process connects the crime scene to the courtroom. It links what happened in reality to what can be legally proven. This educational series on forensic physics is presented by the Physical Sciences Consultorium. PSC is a platform dedicated to explaining science with clarity, rigor, and real-world relevance. Forensic physics is not about chasing criminals. It is about understanding physical evidence using established laws of physics. Whenever a crime occurs, physical processes inevitably take place. Objects move, forces act, and energy is transferred. These processes leave behind traces. Some are obvious, while others are subtle and easily overlooked. A broken object reflects applied force. A displaced item reflects motion. A temperature difference reflects heat exchange. A mark on a surface reflects contact and pressure. Physics provides tools to analyze all these traces objectively. It does so without emotion, intuition, or speculation. In a legal context, this objectivity is crucial. Courts require explanations that are testable and logically consistent. A crime scene may appear chaotic. From a physicist's perspective, it is not. It is a physical system frozen at a particular moment in time. Every element within it obeys physical laws. Every object at the scene has a position. It also has an orientation and a physical state. Nothing exists without measurable properties. This is the starting point of forensic physics. A body has a temperature and mass. A vehicle has momentum and kinetic energy. A surface may show deformation or fracture. Each of these carries physical meaning. Forensic physics treats the entire scene as an interconnected system. It does not isolate objects without context. The goal is not imagination. The goal is reconstruction. Reconstruction means working backward from evidence. It means inferring past events from present measurements. Unlike predictive physics, forensic physics is retrospective. It seeks to explain what already occurred. This reconstruction begins with careful observation. No analysis is possible without reliable data. Investigators must document the scene accurately. Photographs, sketches, and measurements preserve relationships. Once a scene is disturbed, information is lost permanently. Physics cannot recover missing data. This is why documentation is a scientific act. It is not merely procedural. Measurement forms the foundation of all forensic analysis. Without measurement, evidence remains qualitative and weak. Distances between objects are measured precisely. Angles, heights, and relative positions are recorded. Time intervals are estimated where direct measurement is not possible. Mass, speed, and temperature are noted whenever feasible. However, an essential scientific principle must be emphasized. No measurement is perfectly exact. Every measurement contains uncertainty. This is not a flaw of forensic science. It is a fundamental feature of measurement itself. All instruments have limitations. A ruler has finite markings. A thermometer has limited resolution. Human judgment introduces variability. Environmental conditions add further uncertainty. Forensic physics does not ignore these uncertainties. It acknowledges and quantifies them. Uncertainty is reported explicitly. It is included in conclusions rather than hidden. This transparency strengthens forensic evidence. It allows courts to understand reliability and limits. An expert who claims absolute certainty is not practicing sound science. Physics does not deal in absolutes. Instead, physics provides ranges and confidence levels. It defines what is likely and what is impossible. Courts rely on experts who explain both results and limitations. This balance builds trust. Another foundational concept in forensic physics is the reference frame. Motion cannot be described without perspective. A vehicle may appear stationary to a passenger inside it. The same vehicle appears moving to an observer on the road. Both observations are valid. They are made from different reference frames. In forensic analysis, the reference frame must be defined clearly. This definition precedes any calculation. Without a reference frame, motion data is meaningless. Speed and direction lose context. For example, skid marks are analyzed relative to the road surface. They are not analyzed relative to the moving vehicle. Choosing the correct reference frame ensures consistency. It prevents contradictory interpretations. Failure to define reference frames leads to confusion. Such confusion can undermine legal credibility. Forensic physics therefore insists on precision of perspective. Every analysis begins by fixing the frame of observation. Measurement and reference frames provide raw data. But data alone does not become evidence. Forensic physics moves from measurement to interpretation. This step is where physical laws play their central role. Numbers must be connected to principles. Distances, speeds, and temperatures gain meaning only through theory. Classical mechanics explains motion and force. It allows reconstruction of how objects moved and interacted. Thermodynamics explains heat transfer. It helps estimate how temperatures change with time. Material physics explains deformation and fracture. It reveals how much force was applied and in what direction. Each branch of physics contributes selectively. No single law explains an entire crime. Forensic analysis therefore integrates multiple physical models. This integration must remain internally consistent. Trajectory analysis is a common example. Paths of moving objects can be reconstructed from angles and positions. These reconstructions do not produce a single exact path. They produce a range of physically possible paths. Similarly, thermal analysis does not give an exact time. It provides a time window consistent with physical laws. This distinction is critical. Physics constrains possibilities, it does not narrate events. Forensic physics is therefore a science of elimination. It rules out what could not have happened. Scenarios that violate conservation laws are discarded. Physically impossible claims are rejected. This ability to falsify is powerful. It protects courts from implausible explanations. At the same time, forensic physics has limits. Recognizing these limits is a mark of scientific maturity. Physics cannot identify motives. It cannot read intentions or emotions. Physics cannot decide guilt. It cannot replace legal judgment. Its role is narrower but essential. It provides a reliable physical framework. In court, forensic physicists act as expert witnesses. Their responsibility is explanation, not persuasion. They explain methods, assumptions, and uncertainties. They do not argue outcomes. Scientific testimony must remain neutral. Credibility depends on restraint. Courts value experts who admit uncertainty. Overconfidence undermines trust. This interaction between physics and law is delicate. Each system has its own standards. Science deals in probability and uncertainty. Law seeks decisions and verdicts. Forensic physics operates at this interface. It translates physical reasoning into legally understandable terms. Judges and juries are not physicists. Explanations must therefore be clear and accessible. Complex mathematics is rarely shown in court. Conceptual clarity matters more than equations. This does not weaken science. It strengthens communication. Good forensic physics is not about complexity. It is about clarity and consistency. Courts trust physics because physical laws are impartial. They do not change based on who is accused. Gravity acts the same on everyone. Heat flows the same way regardless of circumstance. This universality is crucial. It gives forensic evidence moral neutrality. When applied correctly, physics protects both prosecution and defense. It prevents selective interpretation. However, misuse of forensic science is possible. Poor measurement or biased interpretation can mislead. That is why understanding methodology matters. Physics must be applied rigorously, not selectively. Education plays a vital role here. Both scientists and legal professionals must understand limitations. This series aims to build that understanding. It does not simplify science beyond recognition. Instead, it builds intuition step by step. Each episode focuses on one physical domain. As the series progresses, complexity will increase, but the core philosophy will remain unchanged. Forensic physics follows evidence. It does not follow narratives. It asks simple questions. What forces acted? What energy was transferred? What motion occurred? These questions anchor analysis in reality. They prevent speculation. This disciplined approach is what gives forensic physics its power. It grounds justice in physical law. This series is presented by the Physical Sciences Consultorium. PSC is committed to connecting physics with society and decision-making. Through this platform, science is explained beyond classrooms. Its relevance to law, policy, and daily life is highlighted. If you find this approach valuable, you can support this effort. Please like this video and share it with students and educators. Subscribing to the channel helps sustain future episodes. It allows PSC to continue producing rigorous educational content. In the next episode, we move deeper into applied mechanics. We examine motion in violent crimes. Bloodstain patterns, bullet trajectories, and impact geometry will be explored. Physics will again serve as the guiding framework.